Okay, recording in progress. Thank you to be here again. Let me now share the lecture. And let me start with the technical content. Yeah, thank you, Sarah. Thank you, Sarah, for your participation also. Uh, I am happy, nevertheless, this semester for the number of students, because sometimes some bachelor, this is the first time for Kalman, of course, but also different courses for different courses. The students hesitate to come in general, and then sometimes they 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 interrupt, they let me say drop out, the course, but I hope that this semester you can remain, or the whole group which I see now can remain for until the end. Okay, let me now why I don't see the now. Okay, now I see the memory. Let me share. Yeah. Lecture. Yeah. As I wrote, I improve a little bit, just a few irrelevant aspects. I don't know if you remember voltage, something really not relevant. And nevertheless, I re-upload for you. Yeah, this is the mm, today. Now, let me share. Okay, almost ready. I think you should see the presentation. Last time we concluded with this block diagram in which I try to explain very roughly the concept of the observability. But as I told you, the last slide, I would like to say it was this one, in which I summarized. Remember the matrix A, the matrix B, the matrix C, the matrix D. If you look at the last part, of this slide, because until now we considered just linear systems. Oh, yeah, linear systems. Why not? Oh, if we consider one linear system, at least mathematically. But I told you about, you remember, bank system. I have some example. I will come back on this for you. Uh, in any case, we understood what is the matrix A, what is the matrix B, C, and D. That general expression of the system, which is the first part or the upper part of the lecture, we will see later in the context of the Kalman filter, because one variation of the Kalman filter is the extended Kalman filter, at least in this course. And we will come back on this general expression. Now, I would like to concentrate again on the matrix A, B, C, D, and then I will reconsider this slide, but this time more in depth. Do you remember last time I flesh out this slide in order to introduce the lecture of today? The lecture of today, as I told you, the idea is to go more in depth on the observability in order to build the observer for a system, in this case at the beginning for a linear system. But we will see during the semester that we can also consider non-linear system. About linear, non-linear, I will come back again. But you remember, last time I think I flesh out the idea. Probably you know from math. I will repeat. In linear systems, we can separate the effect of the state x with the effect of the input u, u in p. Yeah, I don't want to say much more on this, but because in math probably you learned, you formalize the linearity in a precise way. At this moment, just for us, the linearity that I can represent everything using a matrix of very important constant elements. You remember matrix A, B, C, D. This is, for instance, the matrix C and the matrix D. Constant element, 1, 0, and 0. Look at this. The matrix A and B minus R divided L and so on. Here, 1 divided L and 0. Now, for not engineers, it's clear that is not easy to understand this 1 divided L, in particular L, or the R. L is the inductance, R is the resistance. I will consider also different example, liability, assets in an economic system, or infected people as susceptible people. Now we can understand a little bit better some constants in this kind of different systems. But anyway, A and B are constant matrix or vectors. This means no changes in the matrix A and B. The elements are fixed. And in particular, also input and state contribution, we can see here. This element, or this part here, is the contribution of the state. You remember the state? I insisted of the concept of state or the states. State vector, X, or states, current, and let me shut down the email system, otherwise you hear something which is not necessary to hear. And also for me, sometimes I have to, so I don't answer. That's the email. Yeah. I separate because you remember the idea is to describe the variation, X derivative, the variation of the states, current and velocity in our case. The variation of the current over time, the variation of the velocity of the motor over time, as a function of what? Of the state, which reflects the energy. Do you remember I told you last time? And what I do in input, U, I, and P. In probably also today, at the end, I would like to show you a little bit an economical system, because probably we can understand a little bit better this concept here. But let me go ahead with the observability now. I will come back on modeling, I am sure. I will do that. Now, look at this. More abstract, more abstract. Look at this system here. X1 derivative from math, equals minus x1. Everything is, everything. The variables, state variables, x1 and x2. X1 and x2 are the state variables. They are function of t. They are function of t. T is the, let me say, independent variable. Everything is defined over time. Everything changes over time. This means the variation of x1 could be everything x1. What is the meaning of everything? You remember, I told you in the economical systems. Now we can introduce again something. I will be more precise on the economical system. I will tell you about an economical system. X1 could be the liability. The liability is the money in the bank system. The liability is the money which belongs to me, but it's in the bank. Please, it's in interesting things. Because I told you, if the money which belongs to me is at home, this variable, money, does not represent a state variable. The reason is that in the bank, because of the interest, independent of what I do, I put money in the bank, I withdraw money from the bank, the money, liability, in the sense, but money, let me say, theoretically, but also practically, will increase autonomously over time. As I told you, x1 and x2 are two possible variables in the bank system. Could be x1 liability, again explained. X2 could be assets, the capital. Or, anyway, the asset is every title, invested title. I'm not expert in economics. Please look at literature, but I will be more precise a little bit later. Now, therefore, our topic or our approach is quite general. Each one could be also infected people in a COVID system. I will tell you a little bit later during the semester because it's a non-linear system, or at least the model which I will present. Each one could be, for instance, the susceptible people. The susceptible people is the people which can be infected. And this means the first equation represents the changes of the infected susceptible people over time as a function of susceptible people as infected. We will discuss together. X2 as the infected could be the infected. This means, again, I try to generalize. In mathematical sense, we need a system. We need a model which describes the system. About the modeling, I will tell you a little bit in this course because probably in bachelor you don't have experience in modeling. No? But anyway, assuming that we have a model, because modeling should be another course. In fact, in master, I have a course, modeling and simulation. Here I have to compact everything. Look at these two equations, two differential equations. Differential equations means, or the mean equations, a dynamical system. Dynamical means exactly that we are in the presence of derivative. Derivative means variations. Derivatives means variation. You remember in gymnasium, no? The derivative, how possible to say, state variation of a variable. I don't know if you remember, but I am repeating. Now, please pay attention. This language here, a mathematical language, which came from, do you remember last time I insisted on this? I have a real system. I tried to describe the real system. Eventually, I can graph a linear system. Remember the motor. Of course, if I have an economical system, a bank system, I cannot direct graph this because it's really the bank system is quite abstract, more abstract than a model. Also, a COVID system, the dynamics between infected and susceptible. I mean, I cannot graph. I can build, nevertheless, the relationships between these two variables. Could be also more than two variables. I will tell you in detail mathematically. But of course, it's not a motor in which I can see. Excuse me, I see in a message in chat. Okay. The topic from the office was that good. Okay. I don't understand the message, but anyway.
I'm sorry, Paolo. That was my message.
No problems, but if it's addressed to me, we have to.
No, it was going to you. I was going to ask you, but I wanted to tell a friend of me that I am planning to ask you, but I sent it in the group in the chat
No
where
problem.
everyone is.
If I do something for you, you have to ask. No problems.
Yeah, but I will ask you later. It wasn't meant to send in the group chat. I'm sorry.
No problem, no problem. We are really a few an interesting group this time. I never expected, but my way to proceed with the group, we will see probably better when I will be in Lüneburg. Is really
Yeah,
to create a familiar group. This in any case, any question, any criticism is welcome. No? Really.
yeah. Thank you.
But you will see, for everybody, of course, that the most important part we will do together at the end or during the semester, during my office hour. I will fix the office hour when I will be in Lüneburg. The reason is typically the office hour is in my lab. But of course, if you cannot come to me, because I have some students who are in Erasmus, we can do also per Zoom, no problems. And in your case, in bachelor in particular, without a large or strong background, I would like to suggest to come to me to perform or to go a little bit together in the project for the examination. Okay, again, we have these two equations. I gave you these two equations. The equation came nevertheless from a description of the system, came from some physical or population considerations. If you think about infected and susceptible, or economical consideration, if you think liability assets and so on. Anyway, at this moment, I give you this. Look, this expression, these two equations, can be translated in another language. You remember this concept of translation, which, in my opinion, this new language, block diagram language, says much more than the equation. Not only in my opinion, because we will see today that MATLAB Simulink is an application of MATLAB, can very well understand this block diagram language, but cannot until now. We can of course implement directly this language here, the language of the equations, but it's more complicated. Now look, this block diagram says exactly what these two equations say. Now we have an error here. I didn't correct here because I had to redo the picture. I didn't have time. Here is U, I, and P. It's the same input like here. Excuse me for the error, but I also last time I told you. How build this? This is important because for the implementation, what happens now? Okay, for the implementation, we need to understand very well this translation from equation. Happens now from equations to block diagram. It's easy, nevertheless. Look, what is the output or possible outputs? Believe me, in general, in general, we are interested to monitor the states or the state variables. In this case, the state variables are x1 and x2. Why that? Because the state variables are the variables which appear with the derivative. Why that? You remember last time, because we want to monitor, we want to describe, we want to control the energy, and better to say the variation of energy. And you remember last time I told you for the motor, this is done using the derivative. Just flesh out the concept. X1 and X2 are the two, in this case, variables or state variables, because they appear with the derivatives. Look, if x1 is one of the output, the possible output, because it reflects the energy, look, between x1 and x1 derivative, we have an integral. Here, I didn't put the initial condition, because also in MATLAB, in Simulink, which is an application of MATLAB, which uses exactly block diagram, we will see today, the initial condition is inside. But anyway, if you remember in gymnasium, the derivative of the variable, if I have the derivative of the variable, if I do the integral of this derivative, and I know its initial condition, I know also the variable. This means x1 derivative as an input. Look, this arrow means that x1 derivative is an input in the block of the integral. This language means integral of x1 derivative. If I know the initial condition of x1, I will have directly x1. I will come back on this with MATLAB. Now, looking at this first equation, we can see from here that x1 derivative equals minus x1 plus x2. This means, let me assume that I have a block. I have a function in Simulink or in any kind of tool which uses block diagram in terms of software structure, I can write here plus minus what? As I told you, x2, we will see what x2 is, minus x1, but x1 is available. Is available from this point because at this point, I assumed that x1 is available. It's an assumption, of course. But look, very important. We have a loop here. This loop states the dynamics of my system. In fact, if you read again here, we have the x1 derivative, which is this variable here, equals minus x1, which came from the output, plus x2, which I have to build now. Try to remember that each differential equation consists at least in one loop. Come on, we can say so. What about x2? But once we understood x1, or this way to translate the x1 dynamics, let me say so, in x1 block dynamics, now for x2, no problems. Because between x2 and x2 derivative, as before, I can put an integral. Because the integral of x2 derivative, if I know the initial condition of x2 equals x2. Please pay attention, probably I forgot to say, this signal here, which is the output of this plus minus, like here, this signal here is the output of this block plus minus. I was not formal, what is the input, what is the output, but it's intuitive. It's intuitive. This plus and this minus represent the input of this block, and x1 derivative represents the output. This means somehow I can say that x1 derivative, for instance here, equals x2 minus x1. In the same way, I can say here x2, I mean, at least is so defined, x2 derivative equals u, everything is in a function of t, I don't repeat, minus x2, because is written here. Basically, if you understand a little bit my way to proceed, I try to translate this information here into another information. Of course, sometimes I was a little bit too fast in the in order to explain, I would like to say, the grammar of this language. The grammar means what is the input, what is the output, but it seems to be intuitive. No? When I say that x2 derivative equals u of t, u input, excuse me for this error here, I forgot the pedix I and p, minus x2. x2 derivative equals u2, u input, let me say, minus x2, of course, is in the definition of the block plus minus, or in general, the block add. In MATLAB is ADD, addition, in the sense algebraic addition. Once we understood this, but I come back to another example. Look at this now. If I measure x2, this means try to imagine that I put my observation, my measurements, let me say, observation not so good, my instrument here. If I measure x2, it seems to be that no possibility to obtain information by x1, because we can see that from here, I don't have an idea, what happens here. Because x2, x1, better to say so, x1, is not connected with x2. The matrix C, the matrix of the measurements, is 0, 1. Why that? Because you remember, C will multiply the vector x. X is not written here, but consists of two components, x1 and x2. And the matrix 0, 1 means that what I am measuring is x2. Look here. C, which is 0, 1, we multiply the column vector x1 and x2, is clear that x2. The same exercise in which I will measure x1, in this case, we have the observability. Why that? Is, of course, isn't an intuitive idea of the observability. Because if I am measuring x1, I am here with my instrument. It seems to be quite clear, intuitively at least, that thanks to this, let me say, line, this is the feedback, basically, I will have information not only on x1, because I measure, but also on x2, because they are connected. X1 and x2 are connected thanks to this, let me say, line, but the line represent what? Represent mathematically that x2 is present or is represented in the dynamic of x1. This means the variation of x1 depends also on x2. We can see. This means if I measure x1, it could be, it will be possible to have information about x2. Before, I show you that if I measure x1, we don't have this possibility because here, in this equation here, or better to say, the dynamics, the variation of x2, does not depend on x1. Here, the matrix C is not 0, 1, but 1, 0, because I am measuring x1. Just to give you an intuitive idea of the observability. Look at this example here. Is another example. We can see here, again, two equations, similar as before, but now if you observe the dynamics means the two equations, we can see that x1 is here, but also here, x2 is here, as here. This means the system is totally coupled because the two variables are present in the two equations, or channel. In some books you can find channel, no? Channel 1 and channel 2, equation 1 and equation 2, dynamics of x1 and the dynamics of x2, just to tell you about possible nomenclature or way to say or to represent. What is the difference? This is extremely easy now to represent this, because the difference is just that as here we have this line, which from x1 is going to the dynamic x2 with a minus. Why that? Because we have a minus x1. Look, before we don't have this minus x1. Minus also plus for the observability is not relevant. Very important that is there. Should be present, must be present, must be present. At least in this structure here. If I add here minus x1, I will have these two equations. Now, the block diagram does not change, but I have to add just this line, which connect the dynamics. The dynamics is this, let me say, two elements with the feedback. This dynamics, the dynamics of x1 with the dynamics of x2, in accordance with what is written here, minus x1. Now, I can measure x1, I can measure x2. We can see that the system is observable independently what I am measuring. Why that? Again, if I am measuring x1, I have information about x1 because I am measuring. But as before, thanks to this line, I didn't change the equation 1. I can have information about x2. If I am measuring x2, now it's different because I can get information about x1, yes, because I have a disconnection here. It doesn't matter plus or minus, no, for the observability. Very important that the information came from the dynamics of x1 into the dynamics of x2, if I want to measure x2. Of course, here, measuring, as I told you, let me see, here at the beginning, measuring x2, we have seen that the system is not totally observable. I forgot to say totally, but should be better if I say totally, because x2, if I measure x2, I can get information of x2. But the system is not totally observable because I don't have information about x1 in this configuration. But of course, if I'm measuring x1 and x2, the system is observable. But of course, if I measure everything, it's trivially observable. It's trivially. Why that? Because the idea of the observability, and in particular to build an observer, and to have information about variables which I cannot measure, or I don't want to measure. Why I cannot? Sometimes this variable is too abstract. We cannot put a sensor. We cannot put a sensor. In engineer field, we can understand some induced voltage, for instance. Now I don't have in mind any kind of other example, but during the semester I will bring. Or sometimes it's too expensive, too expensive. For instance, the technical example, I worked with Volkswagen in the project on control of the position and velocity of intake and exhaust valve in a cylinder and in the engine. To measure the position and to measure velocity is too expensive and not safe, because we have to go close this to the cylinder. Because of the temperature, the sensors probably doesn't work well, or doesn't work a long time, for a long time. This means we have to think about to measure something different in order to estimate position velocity of these valves, because I need for the control. But I come back with more concrete example. Okay, let me go ahead. As I told you, is this nice to introduce the concept of totally observable or the fully observable? We can see it here in this possible definition of the observability. The observability concept is quite difficult, believe me, because we don't have just one definition of the observability. Here, for instance, in this possible definition, we used another concept which I didn't define, but I didn't define because I don't have time to define. Otherwise, really, we have to use also particular notation, mathematical notation, but just intuitively. Intuitively, it's fully observable. Fully means totally. No? Means I can estimate, I can have information about all possible energy. About fully or totally, we have seen what is the meaning, no? Because I told you one case in which is not fully observable, and one case in which is fully observable. Not only, we have seen much more. We have seen that, of course, also in this case here, which is basically not fully observable structurally, but if I measure the variable x1, is fully observable. Or better to say observable, because sometimes fully observable means, I don't remember in this definition, and we will look together, fully means independently what I measure. We have to be careful which kind of definition which we consider. But anyway, intuitively we can understand. When I give you the mathematical equations, it's clear in accordance in a possible definition, this is not fully observable, because it depends what I am measuring. If I'm measuring x1 is observable. If I'm measuring x2 is not observable. Here, it's fully observable because does not depend on what I am measuring. It doesn't matter, x1 and x2. If I measure x1 is observable, if I measure x2 is observable. This depends of the definition. Yeah, here it's exactly so fully observable, if and only if. Please pay attention, the definition typically if means if and only if. Here is specified. The states are distinguishable infinite time only through the system output. Here is not specified what I am measuring, but in general means it doesn't matter what I measure. It makes sense. No? Makes sense. But anyway, we have a different definition. Forget about this because we can recognize immediately, and then I will tell you some possible tests. What I would like to emphasize in this possible definition, the word distinguishable. States are distinguishable. We need, before introducing this concept, should be better to define the distinguishability. I didn't put because otherwise I cannot proceed with the course. At least I'm bachelor on bachelor course. But distinguishable, this means that I can recognize x1 with respect to the x2. Very important in finite time. Just using a possible output. Here is not, it's general, but believe me, fully means in accordance on a possible definition, it doesn't matter what I measure. Otherwise, of course, it's not fully because depend what I am measuring. This is an impossible definition, as I told you. Sometimes in some literature they are more. Sometimes also me too. Is more. I try to speak about the observability in more roughly way, but it's not possible to make mistake because intuitively we understood what the distinguishability a little bit complex because means I can realize the difference in between. Just I would like to say this concept here just intuitively at this moment. Now I would like to put attention a little bit more on this because this can help, and it's a little bit more formal. And at the end, what I told you exactly now with these two schemes, we am able to understand this test. This test is basically is a theorem. Is a theorem. In fact, we can see here this necessary and sufficient condition. This recalls at a property. This means in a theorem. I don't have time to demonstrate the theorem, believe me, but I can explain the test which came from a theorem. Look, do you remember I told you exactly a few minutes ago? Let me come back. This is important to understand. That here, for instance, this system here is observable or not observable depending what I measure. Look, here is observable because I measure x1. Here is not observable because I am measuring x2. This means directly that we can say that the observability, at least in wide meaning, forget fully and so on, no? In a wide meaning, it depends on what I measure. If I measure x1, the system is observable. This, 1 second again. This system is observable. We have a question. Sarah, question me.
Yeah, I have a question, but it was with the definition. So maybe you just want to finish and then I can ask. I just wanted to ask about the word finite. Does it mean so it doesn't have to be defined, but it has to be finite time?
Very interesting.
It doesn't have to be a defined time, but it has to be like it has to be finished at some time, right?
Right, exactly.
Okay, then I get it.
I didn't insist on this because this is really complicated. Finite time, definite time. This means you don't have to wait at the end of the universe to see the differences. Yeah, it's a little bit complex this, yeah, but I think you understood. Somewhen, what is the meaning of finite
Yeah,
time?
that it's like it's going to happen. Like
Yeah,
there is going to be an ending point,
an ending
basically.
point.
Okay, thank you.
But thank you, Sarah, for your question. The idea to show you this definition, sometimes I have doubts to put this definition in an intuitive way because also the word distinguishability or distinguishable in this case should be defined before. Therefore, to explain a little bit intuitively is difficult. Also, finite time, but you understand exactly. I mean, I would like to be happy in my life and not after my death. In the sense, a little bit, I try to trivialize the concept. We have a time which I can distinguish both. This is it's a little bit a mathematical sense. Sometimes I don't want to put this definition because I have to define what is the meaning of finite time, I have to define distinguishability, but sometimes it's useful to say we have really formal definition. I avoided here the mathematical notation, just to give you just feeling, just feeling. Thank you for questions. But in any case, I would like to say here, it's clear that in a wide meaning, forget fully, total, it doesn't. If I measure x1, fix the important idea. If I measure x1, the system is observable. I hope that I explained well. If I measure x2, the system is not observable. This means, of course, the observability depends what I am measuring. If I remember that what I am measuring is mapped through the matrix C, really also to the matrix D. You remember here. Y, what I am measuring, depends of C multiply the state plus D multiply the input. But in this course, I will consider always D equals 0. Now question is always D equals 0 in the real system? No, but I don't have time in the course to tell you about D not 0. But in the project, we can do together because it's not extremely difficult, but I don't have time to explain, of course, everything. Or anyway, I have to select some I would like to say more important aspect, or more important I don't want to say, but basic aspect. It's not much more, but I don't have time. But believe me, if I am happy if you can consider a project in which D is not 0, why I'm happy? Because this demonstrate me that we can do something also different. I mean, with my background, believe me, we can do really complex, more complex system, more complex than what I am explaining during the lecture. This means we can consider also in the project D not 0. Now, at this moment, D is 0, at least in these examples, because I am measuring x1, I am measuring x2, just the state. But in some cases, it could be more complex, the structure of the sensor system or the sensor map. We can see that C maps what I am measuring, at least in our examples. This means now we are not surprised if in this test, now I will tell you about the test. We have C with weights, or the play, let me say roughly speaking, an important role in the test, or in building this matrix Q. We can see a C at the beginning, then C multiply A, then C multiply A squared, and so on, until C, which multiply A up to n minus 1. Now, I don't want to show how this matrix is built, but intuitively, it's quite clear that we have also the matrix A. At least this is clear. Why that? Because if you look at this example, also the previous example, it's blocked. No. Yeah. We can see that the connections between the state play also a role. Why that? Because between this example and this example, now I have a connection more, and of course, with the connection more, change the concept. The concept, no, but if the system is observable or not. In this case, I told you, in accordance with some definition, this is fully observable, independent of what I am measuring. This means we can understand that depends of C, what I am measuring, but depends also on the structure of the system. And the structure of the system is characterized by the matrix A, the transition matrix, because the transition matrix A states the connection between the state variables. No? Of course, A squared, and so on. This is a little bit more difficult to explain. But let me say, depends how many state I have. This matrix Q. We can see a little bit because n I didn't write here in order to be a little bit more compact, but is the number of state. It's clear a little bit this. It's clear a little bit this because if I have a more state, could be more difficult to be estimated, not this to obtain the observability, because I need connections, enough connections. This means intuitively we can understand this A squared until A up to n minus 1. But of course, in order to understand exactly who, I have to show you the demonstration of the theorem. I don't want to do that, but I would like to say a little bit more about the test. Isn't a theorem which is sufficient and necessary condition, or better to say necessary and sufficient condition. We will see that if the system is not linear, we cannot say the same. Not only. But let me go ahead. What I would like to say, that the test says that the matrix Q, which is built with this in this format here, says that the system is observable if the rank, I don't know if you remember the concept of the rank of this matrix, equals n. N is the number of state, full rank. I will do with MATLAB some exercise for you, no? So we can understand better. What is the meaning intuitive? Intuitively, we can say that I will see through the matrix C, I will observe, I can estimate all variables, but of course, using the matrix C. If it's observable for each matrix C, this means it's full observable. We are speaking about this. I told you I was not exactly precise before when I told you about the linear system, because of course a linear system could be also time variant. What I told you before, I called before linear system, but to be precise, I have to say that what I told you before is a linear time invariant system. This means if the element of the matrices A and B are depend on the time, it does not mean that the system is not linear. The linearity is given just is given by the separability. I can separate the effect of the state in my output, x derivative, for instance, from the effect of the input. This is the linearity. Now, what I told you before, if A and B are constant, it's linear, but I would like to add, I must add time invariant. If A and B depends of time, we have nevertheless the linearity, because I can separate these two contributions, the contribution of X state and the contribution of U, but A and B change over time. This means we have in a system time variant, nevertheless linear. A little bit complicated, I would like to say, in the nomenclature, but I will come back on this. I will come back because when we will build with Kalman a couple of exercises, this should be really more clear than now. Now I try to give you just feeling. We are speaking about linear, yes, because we can separate the contribution in output between state and input, internal energy states and external energy input. Do you remember I told you last time also in the bank we can understand very well the internal energy is the liability, and also assets, and the external, what I put in input, what I invest, and what I eventually withdraw. Could be also linear time variant, of course. We will see a little bit. But let me do something easy now. Linear time invariant. Now, just to flesh out, because now we are speaking about time variant, in case we have a time variant, we can see now that the difference. A of t, B of t, basically also C of t, theoretically at least. Could happen. The test change a little bit. I don't want to tell you about that, just to give you the information that changes something. But what remains, that the theorem is also necessarily efficient because of the linearity. Don't learn about this. Eventually, we will consider in the project together. The message of this slide is just to tell you that a little bit, at least theoretically, but I will go in depth with the Kalman filter, extremely important. The difference between time variant system and nonlinear. Extremely important to understand this. At this moment, just to flesh out that can exist linear time variant. This means that the parameter or the element more in general, the matrix A, B, and C depends on the time, change over time. But the linearity is nevertheless remain if I can distinguish the contribution with respect to the output, x derivative, our output, or in general, x, through X derivative, I can distinguish from internal or the state contribution and input contribution. If this is the case, look, we have always in a condition if and only if. If and only if, for the not engineers, I tell you again, if and only if means necessary and sufficient condition. This means, let me come back on this in order to explain this. This is if and only if, yes, because it's necessary, sufficient condition. This means that if we have rank equal n, it's sufficient to say that the system is observable. Or better to say, the model of the system is observable. Please pay attention to these differences in the language. The model of the system is observable. Why that? Because we test through matrix A and C, which is the model, it's not the system. The system, God knows about the system. We have just a representation of the system. In fact, we have matrix C and A. To be precise, the model of the system is observable. This means if the rank of this, I do with MATLAB together, no? If the rank is n, is enough, is sufficient to say that the system, the real system, the model of the model of the real system is observable. But the condition necessary say that if the system is observable, then the matrix Q is full rank. This means rank of Q equal n. The condition is in both directions. The engineers or the mathematicians understand very well what I intend, but I try to tell you for this concept to everybody. This holds also for time variant. No? This slide here tell us about the time variant. The condition is a bit different. Don't learn now. Don't learn now. Just to inform you that change something, but not change the structure of the theorem. The sense necessary sufficient condition, because nevertheless is linear. The system is linear because I can distinguish the contribution with respect to the output, which came from state and which came from input. Okay, now observer. Now we try to go in depth of the observer because we have an idea about the observability, at least in case linear time invariant and linear time variant systems. Look at this. On the left part, we have a representation of our system. A similar representation we have in the right part. In the left part, we have a continuous representation of a system. In the left part, excuse me, I would like to indicate what I intend for left and right. I have always problem with the connection. 1 second, because I think it's not connected, the memory. Second, I try to fix. I try to move the memory in this position. Just a second, because I'm not. Now, give me 1 minute. Where is now? Yeah, probably. No. Computer. Oh, by this problem now. Now, look, my hand. In the left, let me say left. A, B, C, this is the representation of the system, because we are speaking about observability of the model of the system, no? In continuous form. Here on the right part, we have another representation of the system in discrete. About continuous and discrete, I will come back later. Very important, because we will see the Kalman filter, which I will consider is discrete. But at this moment, I would like to insist on the concept of the observability and the observer, the relative observer. Look, I'm introducing here the concept of open loop observer. Basically, the open loop observer is an artificial copy of the system. Assuming that now another important consideration, assuming that this yellow, let me say, block with A, B, and C represent, please pay attention here, extremely abstract, the real system. Represent exactly the real system. This means I don't have, let me say, error between the representation and the real system. It's totally abstract. Now, this block here, if I am able really to know exactly A and B, which represent exactly the system, is an observer, but is an open loop observer because reflect, of course, what happens in the system, because this hat is exactly, X hat is exactly X. If I know exactly the initial conditions of X, because I know perfectly the system. Again, this yellow block is exactly the system, real system, which is exactly, let me say, represented by A, B, and C in case of, if I consider the sensor. If I know exactly A and B, I can observe X. I will call you X hat. And please pay attention, if I know the initial conditions, I can say that X hat equals X. Why is artificial copy? Why artificial? Because I will never know exactly A and B, or better to say A and B, which represent exactly the system. Forget at this moment the discrete. I will come back later. Look, here's the Professor Lundberger, which started with this theory of the observer. The name Lundberger observer came from the professor. Look now, always concentrating on discontinuous at this moment. This kind of observer is not anymore an open loop observer, because we can see that we have a C block, or better to say, the block which state the possible output. And then look, we have what I am measuring minus what I am measuring the observer. We generate an error between y and y hat. Y hat is what I am measuring the observer. And then I will try, we will see in MATLAB now, to correct what? You remember what I told you before? Of course, X, let me come back 1 second. X hat equals exactly X if, let me say, and only if I know the initial condition of X. Assuming that I know perfectly A and B, therefore is artificial. This kind of observer correct the initial error of X, but of course, assuming that I know perfectly the system. What is the meaning, assuming that I know perfectly the system? Means that I know perfectly matrix A and matrix B. Also in this representation, the block in the yellow block is exactly the model which reflects exactly mathematically or physically everything perfectly represented through the matrix A, B, and C. A, B represent the dynamics, C represent what I'm measuring. Or better to say, the output of the system inside the block, the yellow block, which is the same C, which reflect again what I am measuring. Give me 5 minutes, then we relax the lecture. Forget again this part here. We will see next week. Let me recap a little bit. Let me do a couple of calculations, and then the last 15 minutes, I try to introduce MATLAB. We will continue also next week with MATLAB and implementation of what? Lundberger observer. Because once we understood the Lundberg observer in continuous. Then I will tell you extremely fast about the discrete structure. And then I think after next week, as I next week a little bit also, we will start slowly with the Kalman, which is discrete, at least the Kalman which I present in this course. Why that? Because nowadays we implement everything in the microcontroller. We use the computer for any kinds of applications, and then it makes sense to speak about the or the to tell you about the discrete form of the Kalman filter. Basically, the continuous form is just in a theoretical, analysis, because I have seen in my career always the Kalman filter implemented in also in theoretical analysis in discrete form. To sum up, what is a closed loop observer? The closed loop observer, we try to estimate, look at the system sigma. This is the real system. I did it's less abstract as before. Less abstract than before. Do you remember? The real system before I told you is representable using matrices A, B, and C. At this moment, it doesn't matter what is. I have a model. The model is a mathematical. Do you remember? Model in our case is a mathematical structure. Okay, last time I told you model is everything. We have also a model of a cloud. We have a model, anyway, now in our case, in mathematical expression. Yeah, this means I measure something. I can measure also everything. But of course, if I measure everything, sometimes the question is, but if I measure everything, why I need an observer? Because I told you an observer is important, is more important if I cannot measure everything, but can be used also if I measure everything. In particular, an optimal observer. I will come back on this, because what I am estimating is better than what I am measuring. It seems to be strange, this concept here. But if you think about the word filter, is quite clear, because I filter what I don't want. The measurements are always affected by errors or faults or something which does not belong to the dynamics of the signal, of the system, excuse me. But I will come back on this, a very important thing. Also mathematically, no? I told you the theorem of Gauss-Markov. What I am observing under some hypothesis is better what I am measuring. Fix the idea here just roughly, but important. I have a block L, which allow should be designed. I don't know if I have time today. Let me start netless. I will calculate L. In order to observe X, everything X, even though I don't measure all, assuming that the system is observable using C sensor. C sensor means the map of the sensors represented by C or reflected by C, the matrix C. I can, as I told you, observe everything, X1, X2, X3, in this case, or Xn. And with L, I can speed up, I will clarify now in 1 second, the observation. But thanks to this feedback, which generate an error between what I am measuring, at least one variable, and what I am observing, which is C multiply X hat. C multiply X is what I am measuring. C multiply X hat is what I am observing of what I am measuring. Let me look together with you. Give me just a few minutes. How many slides? This, in order to blocked again the presentation. Second. Always blocked. today. Okay, now. It doesn't work. No. This slide, 2 slides, 3 slides, and then I try to open MATLAB until here. Few minutes. Look at this. We have a real system, sigma, which I assume to be known perfectly through the matrix A and B, but and C, excuse me, but its representation, which is in the lower part, of the slide, is affected by an error in its initial energy. This means x0, which we can see here, which is the initial condition of the energy of the real system, is x0. Is what is it? But in its representation, not exactly the same. I mean, the idea is I know exactly the system, but I don't know the initial condition of its state variable. This means I don't know the energy. In electrical system, I can do a couple of examples. One of them is, for instance, I want to, I measure, as I told you last time, voltage and the current in the motor. But I don't know, for instance, the initial condition of the velocity, for instance. It's exactly what I am trying to represent here. It's not exactly known the initial condition of the velocity. But I know exactly the system. We can see the matrix A is the matrix A of the observer. The matrix B is the matrix Z of the observer. The matrix C of the system is the matrix C of the observer. If you look at the scheme here, which is a little bit better, in my opinion, than the scheme here on the left, now the observer, or a possible definition of the observer, is to add another input. Look here. Here, to the model, we have a U input, but we have also another input, which is L multiply the error between what I am really measuring, at least one variable, and its, let me say, observation, because it's C multiply X hat. Hat is the observation. Huh? When I select from the observer vector exactly what I need in order to compare. The idea is to correct the dynamics through L, which must be designed, using the error between what I am measuring, let me say, roughly speaking, I am observing, in the sense of the measurements. This means we have two inputs in the observer, this here and this here. A few words about that. Look at this. In the first line, we have the observer as I defined, or I try to introduce. Then I am considering y equal y of t, of course, equals c multiply x, and y hat equals c multiply x hat. If I plug in these two equations here, if I plug in instead of y, the c multiply x, instead of y hat, c multiply x hat, I will have this expression here. This was exactly my system, which is reflecting exactly, totally, artificially, if you like, because I will never know the system. This we will see later. We will see later with the Kalman filter. But assuming that I know, was the system. Now, subtracting the equation of the observer from the equation of the system, we obtain this equation here. Please pay attention, here is the last thing. If I do this equation minus this, I will have x dot minus x hat dot equals a, which multiply x of t, or the x in general, minus, remember, this equation minus this equation. A multiplies x hat minus this. In particular, minus this, because I already substitute this position here, y equals c multiply x, y hat equals c multiply x hat. I have this. Look here, if you put in evidence A here, we have A parenthesis x of t minus x hat of t. Clear, no? I can put in evidence also this C. I have L multiply C, which multiply x minus x hat. But if I define x of t minus x hat of t as the error of what? Observation error, which in this case depends just on the initial conditions, because everything is no. In particular, I would like to show you that the element b multiply your input through, when I do the subtraction, cancelled. But this is cancelled just if I assume that I know the system perfectly, in particular the matrix B perfectly. Do you remember in the model, the matrix B depends on L. This means I have to know this parameter L inductance. Very important to understand this. Now, if I define the observation error, which depends just on the initial condition, E of t, the error of t equals x of t minus x hat of t, is written here. No? I will have this expression here, which is the dynamics of the error, or better say the observation error, which in our specific artificial example or explanation depends just on the initial condition. We can see here. A of 0 equal x of 0 minus x hat of 0. We have a difference in between. I assume in order to show you the concept of the observer. But please pay attention, if you remember in math, at least for engineers. For not engineers, I will try to explain. When this error is going to 0, even though asymptotically, in this case, we are speaking about an asymptotically observer, or asymptotic observer, excuse me, asymptotic observer. If I am able to place, very important concept, the eigenvalue of the matrix A minus LC, LA minus LC, with real part negative. I don't know if you remember, the engineers probably know this concept here, or at least the engineer who attended my dynamical systems classes. But for the non-engineer, it's not so extremely now important to go in depth on this. In any case, depending on L, this is the concept, depending on L, I can realize a converging error to 0. This means if E of t converges to 0, this means that x hat is approaching, or they converges on x of t, even though asymptotically means in infinite time. I am building an observer in infinite time, even though, do you remember the concept, the observability is defined in finite time? That this is a little bit a mismatch, it seems to be a mismatch, but believe me, we can also build an observer in finite time. It's not the case. It's not the case because it's too complex until now, or in general, in bachelor, let me say. For the students who attended my classes in dynamical system, for instance, the sliding mode observer is in finite time. In this case, we are speaking about something a little bit abstract, but it's not so abstract because we can nevertheless speed up the observer as we want using the matrix L. But of course, we need nevertheless infinite time. But practically, we can implement because in some application, if the difference is practically nano dimension, nano means 10 up to minus 9, or the pico, or sometimes micro dimension, 10 up to minus 6 is acceptable for the application. Why that? Because very often this isn't a problem of the model. this is the problem of the model, because the model is an abstract model which does not consider some elements, some losses element, some loss elements, and then in the real case, we have a convergence which is finite, even though mathematically, because of the representation, it seems to is mathematically in infinite time. Okay, I have just 5 minutes or something like that. At this moment, I would like to stop here because today I told you a little many things in these 5 minutes. Nevertheless, I will open MATLAB, and I will start a little bit to introduce MATLAB because I know that not all students in this course. I mean, I think that somebody of you does not know MATLAB. And then next week, I will tell you about, we implemented this. We implemented really MATLAB. We will test also this rank of the observability matrix. We will do some considerations. And at the end, nevertheless, I try to introduce some concept on Kalman. And before I have to tell you about the discrete systems very shortly, because I have a discrete let me say, having a course in master on discrete systems, but of course, discrete systems sometimes really is a master course. This means here in this course, I try to give you some ideas, some idea of discrete system. Give me a couple minutes to introduce MATLAB for students which don't know absolute MATLAB, and then next week we started directly with the implementation of this element which we have seen today. It is an introduction. It's an introduction of Kalman. Nevertheless, one word. Today, and we will repeat next week. We have seen today the connection is. We have seen some conservative hypothesis. Conservative means. Do you remember I told you I know everything? With matrix A, B, and C, we represent perfectly the model. Kalman field helps to relax this hypothesis. You know what I understand? Conservative, relaxation. Conservative means it's clear. If I know everything, to build an observer is not so difficult. In this case, what I don't know was just the energy, the initial energy. No? In fact, we have seen that relatively easy. We will see the implementation. We have an observer, at least mathematically, but I will implement, believe me, I will show you exactly. Kalman filter helps to relax this conservative hypothesis because Kalman filter say, if I don't know perfectly, it does not matter. We can arrange nevertheless an observer. It's a very important element because the word artificial is related to this hypothesis because of course it's artificial to say I know everything because it does not exist really to know everything. Then we didn't consider here faults or noise. Fault or noise means something which is not related to the model, something which is related, for instance, to the measurements. The measurements can make mistakes. This means I bring in the observer something which does not belong to the real behavior of the system. Let me clarify this again, if I'm able to share. Look at this. This C here is the C of the observer in the representation of the observer. It's a little bit strange, this picture, but I clarify the meaning of this picture. This C in this picture here represent exactly the physical sensor. Basically, we have a matrix C. It's not a good representation, but in any case, in this representation says that Y came from a sensor. Of course, we can represent also a different form. And what we have here in the dashed element is exactly the software. I mean, I have a measurement, and then of course we have also some electronic parts or some parts which try to adapt, at least in technical system, what I am measuring with the structure of the microcontroller. But in this picture, this dashed, inside this dash is the software. Now, what I would like to say that the sensor can make mistakes, can introduce faults. In this connection, we can have noise because we are working in a noisy environment, or in general, in the data, in the measuring data, we have errors. Also in the COVID structure, because we measure, for instance, we receive data from the health office about the infected people, but this could be affected by errors, the data which we received, because it's not precise, because sometimes they approximate, sometimes it's referred a different time. Anyway, it's clear that in the data we can have errors. Errors and noise. I will come back on this in the future. One couple minutes, let me open MATLAB. I don't have much time, but let me open MATLAB. What we will see next week, we try to implement what we did today. Where is MATLAB? Huh. Oh, to find now MATLAB. Let me, MATLAB, found it. If I click twice on the icon, please, an information for you. You can use all research from the university. We have the research license. If you need to start, it doesn't matter when, tomorrow, today is too early, next week or at the end of the semester. And if you want to use our research, software research, send me an email, and um, I will forward this email to our technician, and he will answer how we can use this. All students can use our research. We have licenses. We pay 30,000 euros per year to have all possible license. You can use this from home. I will forward your data to Detlef. Detlef is our technician, and he will tell you it's extremely easy. Or you can speak with some students who already used. It's not so difficult, but I think Detlef should activate something. I am not sure about that. But anyway, until now I did so. And then you can really, in a comfortable way, from home, to download, first of all, my software, and to try to repeat again what I told you during the lecture, and to modify something, to disconnect something in order to understand what we did together. I think we don't have much time. Once you, just a few words, and then next week, of course, we will go really in depth. Let me open it's extremely slow, but I would like at least to open MATLAB. MATLAB is one of the most important software in the context of simulation, modeling, control, signal processing. Of course, we can use also a different software. In companies, very often is used Python. But believe me, if you learn MATLAB, this is a plus in your CV. Very often, let me share, very often in some positions is required explicitly MATLAB. Look at this. Just a few words. This is MATLAB. Click twice on the icon. The icon is written MATLAB, basically. I didn't show you the icon. This is the basic window once we click twice on the icon. Just a few words. Now we will see next week. Look, here And this MATLAB here is in a window structure, or runs under Windows. This means something is probably familiar. We can see at the path where we are. At this moment, we are the part which I worked together with some students in the PSO. In the middle, here in the middle, we can see in a very complex software. We will see during the semester something similar. We can really use MATLAB as a support for programming. We can see the .m, .MATLAB. MATLAB means matrices laboratory. And therefore, I introduced also last time or today also we have seen a little bit matrices. Extremely important because also Kalman filters, everything, let me say everything is matrices. A table of value of variables could be also time invariant. You remember this. Forget at this moment this central part. Here we have the command window in which we can write, for instance, 1 plus 1, 11 plus 1, excuse me, equals answer equals 12. We can use this environment for different tasks, in particular to call M file, which I can write here. Look here. On the right, we have a workspace in which we can see the variable which is present in the workspace. The workspace is the kernel of MATLAB. Basically, the workspace means which variable is active on MATLAB. Look here, we have also ANS answer 12. It's a variable, ANS. On the left part, let me say left is basically the folder, no? The current folder. We can see in this case, we have a folder, which is this one with the path. Next week, we will generate our folder, no? With our files. From here, we can also call, we will see next week, an important part of MATLAB, an important part of the course, which is Simulink. Simul is also MATLAB, but is in a graphical interface in which we can implement, let me say, our block diagrams. Therefore, this week, I insisted a little bit with this language, block diagrams. Let me stop here for this week. Next week, we will repeat a little bit this MATLAB and we'll implement, and Lundberger observer, we will go in depth on this. We will go in depth with the test of the observability. We will go in depth on the structure of this asymptotic observer, which works in infinite time. But we will see it is not a drawback and a big drawback. We can also observe infinite time, but I don't have time in this course, because a little bit more complex. The reason is, we have seen that an observer, the last sentence, is in a controlled system because of the feedback. Let me open again the file. Please keep in mind, an observer is in a controlled system. Look at the scheme. Controlled means I am measuring something and I am comparing with what I am observing. Look at this feedback here. This error here represents the effect of the feedback. It's in a controlled feedback. In order to obtain a finite time observer, we have to build this control system in a particular way, but this belongs a little bit more in control systems, and here we are more oriented in observation, observability, and in particular, the observer as a Kalman filter in its basic and some variations of some variation forms. Okay, if I have a question, I may hear for you. Otherwise, I will stop to record, and we will see next week, same times. And let me
Sorry.
look. Sarah, ask me.
I just have a question. So next time we're also going to be online, or is the
Yeah.
seminar?
It's
Okay.
online. Excuse me again. I have the permission until at the beginning of November,
Okay.
the first week of November. I don't know if I will use all period, but I will communicate when I will be present.
Okay, perfect.
As long as I don't say anything, and I mean, at the end of the lecture, I say always, we will see next week in online. This means next week we will see again just online. But relative at the beginning of November, I think the second week of November, in any case, because I don't have the permission to continue just online. It could be that I will come back earlier, but I will communicate
Okay.
also per my study. At this moment, next week, again online. I know that's a little bit complex, but in any case, the course remain hybrid. This means I will be somewhere in Corazzuse, but nevertheless, you can hear me also per Zoom. Next week, just online. This no in Corazzuse. Other questions? Okay. If no questions, I
Oh,
will.
I have one more. Sorry.
Yeah.
I just have maybe you have some suggestions, like some material, additional material to like get into the topic as like a non-engineering person. Maybe some basic things also for understanding. Maybe do you have some tips or like YouTube videos you could maybe put on my study? So yeah, that would be very helpful for me at least.
Sarah, did you have difficulty to follow me a little bit?
It was okay, but still, but sometimes I was like, okay, I would like to know more about it. And yeah, also like more in depth, like fundamentals, I think. I just
Mm,
wanted to ask if maybe you have
yeah, yeah.
something you can put up on my study or something. Yeah.
About my study, I'm not sure if I have to look for. Now, let me stop to record. Let me see.